Hi, good afternoon students. Today I will be discussing about a wave. So what is that? That is standing wave. So that this is my aim, the discussion on standing wave. So actually we know what is standing wave. Why this wave is called like this. So we should remember one point. One point is this is not a general wave. Okay, this is only developed at particular situations. Okay, so first we can brush up the general thing happened in the wave. So that means the first point. So if one thing is said to be a wave, then that must be satisfied what? We know linear wave differential equation. So what is that linear wave equation? So a wave must be satisfied linear wave differential equation. Okay, linear wave differential equation. What is that expression? That expression is equal to dy by d square y by dx square. Okay, x square is equal to 1 by v square into d square y by dt square. Okay, this is that expression. So in here, what is v? V is the velocity of wave. So v is equal to, or we can represent like that, omega by k. V is what? Omega by k. What is omega? Angular frequency. And what is k? That is angular wave number. Okay, this must be satisfied. Okay, a wave is that means a wave must be satisfied this situation. Then only it is called a wave. Okay, then what is second point? So wave, or we say generally a traveling wave. So wave means a traveling wave. So what does travel in here? The particle is traveling? No, it's absolutely incorrect. Actually we know what is traveling. Energy is traveling from one point to another. Okay, so energy is actually traveling and particle is only oscillates about its position. Okay, particle is only okay. So another thing is what is the general expression for a traveling wave or traveling wave? That is for a traveling wave, this is like a function of t minus x by v. So there's a function, this must be a function of t minus x by v. Then only we can say this is a traveling wave. Then only we can say this is a traveling wave. Okay, then another thing is the third thing. And this, just imagine, and this wave, this traveling wave is traveling wave incident on a any fixed or fixed end or loosely loosened or free end. Okay, so at the time we know that this wave will be reflected back. So I am considering that point. That means reflection. In the case of reflection of traveling wave. Okay, reflection of traveling wave from fixed end. Okay, fixed or free end. So what happens? So let's check. So reflection of traveling wave from fixed or free end. So at the time, okay, free end. Okay, at the time, look here, I am considering first one in the, if the reflection at if it is at a fixed end, what happens? Let's check first that. Okay, at fixed end. So at fixed end, just to consider, this is string. Okay, string, and this is fixed end. Okay, this is fixed end. just imagine a pulse is created here. Just imagine a pulse is created here like this. Okay, pulse is created like the, what happens, it move towards the fixed end. Okay, then after this what happens, we should remember, after this what happens, this will be like this. So reflected wave will be like this. What happens is that this will be inversed due at the fixed end. Okay, that means what is the phase difference between this incident wave and the reflected wave? That is pi. So if a wave is, a traveling wave is incident at the fixed end, then what happens, this will be turned, or the phase difference between these incident and reflected wave will be pi. Okay, so if this displacement equation is y and this displacement equation is y2, then if y is equal to a sine omega t minus kx, okay, then what is y2? What is y2? What is the displacement equation of reflected wave? What is a we can represent by r, and this is I, incident, and this is r. Okay, for the convenience, for our convenience. Okay, then this is our reflected wave. How we can write? That is, reflected wave also has a same a. Same a means there is no energy loss. There is no energy loss. Okay, at that time. Okay, we only have that situation. Then into sine. What is omega? That's a frequency. Depends on frequency. Frequency only depends the source. So source doesn't change here. So omega still same. But just to check the direction, one is like this, another one is like this. So this is plus. And what about, so omega t plus. What about our kx? K is 2 pi by lambda, and we know the both are moving in a same medium, so velocity is not changing, frequency is not changing, the wavelength also doesn't change here. So this is also kx. Then another thing we know, what happens, this will be, there is a phase advantage of, that means reflected wave has phase advantage of pi, so plus pi, or we can say that, or just apply the trigonometric operation, we finally we get minus a sine omega t plus kx. This is the reflected wave expression. This is the reflected wave expression. Then just to consider another thing, that means at free end. So just to check at free end. Okay, at free end. At a free hand, and this is our string, and this is connected at a loose end, this is connected at a loose end, okay. Then in here, if a wave is generated, okay, and I am assigned by yi incident, the displacement equation is yi, then after hitting at this wall, what happens, this is a free end, what happens, there is a no phase change. So there is no phase change between incident and reflected wave. So this is actually our yr. Okay, this is actually our yr. So what is our y incident here? What is y incident here? If this is a sine omega t minus kx, okay, then what is reflected wave? That is amplitude is still same, then sine omega t plus kx, y plus, only this term will be changed. Omega same, frequency same, wave velocity same, so lambda is same, then plus direction is opposite. So that is a reflected wave. So these three things we should remember before going to our standing wave. Okay, then we can start our standing wave. So what is standing wave? So we can define standing wave. So standing wave is actually developed or generated by the superposition of two traveling wave. That means the situation is like this: if two traveling wave having same frequency and preferably same amplitude. So it's not a necessary condition, but we have only this situation. If the two waves having same frequency and same amplitude are moving in opposite direction and superimposed, then finally what happens? We get a one resultant wave. That resultant wave is known as what? That resultant wave is known as standing wave. So we can define that. We can write the definition. So what is standing wave? What is standing wave? Standing wave is, students, what is standing wave? When two traveling waves, when two traveling wave, when two traveling wave having same frequency, okay, same frequency and preferably same amplitude. It's not a necessary condition. Same amplitude or amplitude move in opposite direction, are superimposed, then the resultant wave, formed is actually, resultant wave formed is known as standing wave. Okay, standing wave, known as standing or stationary wave. Okay, standing or stationary wave. Okay, students. Okay, so that means this is a superimposition of two traveling wave. Okay, so we have to check whether this is a traveling wave itself. Okay, newly formed a wave also, we have to check that. Okay, then so I am consider we can take one situation. Look here, if this is a string and this is connected at a loose end. Okay, it is connected at a loose end. Just imagine, connected at a loose end. And if a one pulse is created here, y1, okay, then this is what? This is, we know this is a loose end, or we can say free end. So what will be the reflected wave at a loose end? We know there is no phase difference between these two waves. So this is our reflected wave. Okay, same like that we know how to draw the displacement equation of these two. Then sir, is it visible? So what is y1? Just to write the y1 is equal to, just write a into sine kx minus omega t. Okay, if y1 is equal to a sine kx minus omega t, what is the reflected wave? y2? y2 is equal to, okay, same amplitude, because there is no energy loss. To the surrounding. So sine, then same k we already discussed, moving in opposite direction, omega t. So the superposition of these two waves is actually the resultant of superposition of these two waves is actually what? Our standing wave. That resultant wave is known as standing wave. So let's try to find. So this the resultant wave is actually y1 plus y2. Just add these two. So y into sine kx minus omega t plus a into sine kx plus omega t. Okay, plus omega t. Just add, and a's are a, two a's are common here, just take outside. This is a what? Then remaining term will be sine kx minus omega t, sine kx plus omega t. So I am going to treat like sine a minus b plus sine a plus b. Okay, so this is actually sine a minus b and plus sine a plus b. That means kx plus omega t, kx plus omega t. Okay, so what is sine a minus b? We know. So well known result, we know that. What is that? Sine a cos b, there is a negative sign, negative, cos a sine b, okay, this is actually sine kx minus omega t, same like that, plus. What is sine kx plus omega, sine a plus b here? Sine a cos b plus then sine b cos a. So this is the, so I have elaborated this expression, just to check. This is a minus cos kx sin omega t is there, cos kx sin omega t is there. So we can cancel these two terms. Finally what we get? We get sin kx cos omega t, sin kx cos omega t. So what is the resultant equation? That y is equal to a, this is 2. So 2a sin kx into cos omega t. So this is what actually, this is our resultant displacement equation of wave, and this is our displacement equation of standing wave. Okay, this is our displacement equation of standing wave. Okay, very important. Okay, very important. This is our displacement equation of standing wave. This is the displacement equation of standing wave. This is actually what? This is the displacement equation of standing wave. Displacement equation of standing wave. And or another term is stationary wave. Why this is called standing or stationary? That means I already said that there is no energy loss to surrounding. So whatever energy is available, that is completely confined here. So that means completely confined here. So in the case of traveling wave, what does move? That means we know energy travel from one location to another location. But in here, energy confined in this region. So that is why we call this as standing or stationary. There is no progression, or there is no traveling. The energy is not traveling. Energy is not propagating or progressing. So this is actually what's a standing wave. Then we know what is the basic thing. We know if a wave is said to be, if wave said to be traveling wave, that must be function of t. That must be function of what? That must be function of t minus x by v. So that means you can't find anything here like that. So that means what? This is not a traveling wave. This is not a traveling wave. Very important. This is not a traveling wave. Next thing is, so I already called this is a wave. So that means if this is a wave, then this must be satisfied what? Linear wave differential equation. So we have to check that. Okay, so we have to check. That's my next aim. I'm going to check whether this is wave or not. Okay, so what is that? We know what is that expression. What is that expression? Expression is, we know, that means d square y by, what is our expression? What is our displacement equation? Y is equal to 2a sine kx into cos omega t. Okay, kx into cos omega t. Okay, then I am going to check the linear differential equation. D square y by dx square is equal to 1 by v square into d square y by dt square. Okay, d square y by d square. So just to find the double differentiation of this displacement equation with respect to x, so 2a and cos omega t is constant, so take 2a, cos omega t is constant, okay, cos omega t. I am differentiating with respect to displacement. Then sin kx is there, just to differentiate what we get to minus cos kx, that means minus cos kx and 1 k is there. Then this is a double differentiation, again differentiate this cos kx, what we get to that is plus. Then just differentiate this cos kx, what we get to minus sin kx. So what we get, minus sin kx. This is a cos omega t. So there is a negative sign here. There is a negative sign here. Negative sign here. This become k square into sin kx. Sin kx. This is equation number 1. The next differentiate. Just double differentiation of this displacement equation with respect to time. Okay, so I am going to differentiate with respect to time. Okay, so this term will be constant. So 2a into sin kx is constant. Then differentiation of cos omega t. What is that? Minus. That means minus omega into sin omega t. We need what? We need double differentiation. We need what? Double differentiation. We need double differentiation. So again differentiate this one. What we get? We get just a differentiation of sin omega t. We get cos omega t, omega into cos omega t. This is expression 2. This is expression 2. So just to divide these two. So what we get? That means d square y by dt square upon dx square upon, okay, 1 by 2, okay, dx square divided by d square y by dt square. That is equal to, this is cos omega t sin kx. So cos omega t sin kx, both are present in both equations. So 2a k square divided by minus 2a k square divided by minus 2a omega square. Finally we get what? What is k square by omega square? So we know omega by k is v. V is the velocity of wave. So what is this one? This is a 1 by v square. So this is what? This is the 1 by v square. So our final expression is what? D square y by dx square is equal to 1 by v square into d square y by dt square. Okay, d square y by dt square. So that means it satisfies. That means what we can say? We can say that it satisfies. It satisfies linear wave differential equation. Okay, linear wave differential equations. Okay, so it's not a traveling wave, but it satisfies what? Linear wave differential equations. Okay, then another thing is very important. Another thing is, I am going to check the amplitude. That means what is our displacement equation y? The y is equal to 2a sin kx, 2a sin kx into cos omega t. What is that? This is the displacement equation. This is what? This is the displacement equation. Okay, then that is 2a sin kx into cos omega t. That means displacement equation is a something into cos omega t. If a displacement equation is something into cos omega t or sin omega t, then what we can say? That this that means this is a particle displacement. So particle is a standard SHM equation. So that means particles are performing SHM. Particles are performing SHM. But another thing is, so in our SHM chapter, we know this amplitude is what? 2a sin, not like that. So very simple thing, that only a. But in here, this is a 2a sin kx. That means what? This is not a constant thing. 2a sin kx means it depends x. What is the x position of particle from the beginning? That means this amplitude depends x. So what we are getting, we are getting that that means particles in the standing wave oscillate in SHM. Oscillation is there, perform a SHM, but with a different amplitude. But with a different amplitude. That's a main important point. Okay, so that means particle perform SHM with a different amplitude. So that means different amplitude means I am going to check what is the minimum value, what is the maximum value. Okay, so let's check that. Let's check that. That means what is our amplitude, resultant amplitude? This is our resultant amplitude. Okay, that resultant amplitude is equal to 2a sine kx. 2a sine kx. So what is the minimum value of sine kx? Okay, in positive minimum value, that is 0. So what is that? So that is the minimum value. That means, so the resultant amplitude is 0. Okay, I am going to check the range of this amplitude. Okay, so when we get this is 0, that means sine kx is 0. When we get sine kx is 0, that means when kx is equal to n pi, simple trigonometric. What is k? That's a wave number 2 pi by lambda. Just to put here 2 pi by lambda x into n equal to n pi. So after that what we get, x is equal to what? N lambda by 2. What is k? That is wave number, angular wave number, that is 2 pi by lambda. So just to put here 2 pi by lambda, pi will be cancelled, then lambda goes here. So we get x is equal to n lambda by 2. And what is n? N is the positive integer, n is equal to 0, 1, 2 and so on. That means our x value is 0 lambda by 2, 0, then lambda by 2, 1 lambda by 2, then 2 lambda by 2, then 3 lambda by 2 and goes on. That means at these locations we get to 0 amplitude. So this is the minimum value. This is the minimum value, and that means there is no amplitude, means at these locations it doesn't perform any SHM. This is at rest. And this point is known as, nodal point. Okay, this point is known as nodal point. This point is known as nodal point. Okay, nodal point. Then I am going to check what is the maximum value. I'm going to check what is the maximum value. What is the maximum value? Then when we get the maximum, when sine kx, what is the maximum value of sine kx? 1. So what then, if sine kx is 1, what is resultant amplitude? Our resultant amplitude become 2a. So this is the maximum value. This is the maximum value. When we get sine kx is equal to 1, that means kx is equal to, what is that? Simple trigonometry, 2n plus 1 divided by pi by 2. 2n plus 1 into pi by 2. At this value, that means n is what? Any vary from 0 to any positive integer. Then what is k? Just to put what is k? 2 pi by lambda. Finally what we get at these locations. So x is equal to 2n plus 1 lambda by 4. Lambda by 4. And what is n value? N is equal to 0, 1, 2 and goes on. That means at these values we get maximum amplitude. Okay, that means the x is equal to, just to put n is equal to 0. What is this one? What is this one? N is equal to 0. What we get? What we get? We get lambda by 4. Then if n equal to 1, 3 lambda by 4. Then 5 lambda by 4. That means at these locations, what we get? We get maximum amplitude. And this point is known as, that means the point at the maximum amplitude is known as anti-nodal points. Okay, and this is anti-nodal points. Okay, anti-nodal points. Anti-nodal points. Anti-nodal points. So so there is a range of amplitude is, it varies from 0 to 2a. And if amplitude at a particular location is 0, that point is known as nodal point. And if the amplitude is maximum, that value is 2a. What is 2a? That is the double of amplitude of that incident and reflected. That means superimposed wave. That double amplitude. Okay, 2 times of amplitude. So that when we get this value at x equal to lambda by 4, 3 lambda by 4, 5 lambda by 4, or generally we can say 2n plus 1 lambda by 4. So let's draw that graph. Okay, at the time we can understand very well. That means if this is our line, then this is x is equal to 0. Okay, it's a nodal point. The next nodal point is at lambda by 2. Lambda by 2. The next nodal point is x equal to 2 lambda by 2. What is that? That is lambda. The next one is 3 lambda by 2. So these are the nodal points. Then just to draw the graph, this is the graph. This is the graph. Graph is like that. Or like that. This is the graph. Okay, so this is the nodal point, and this at this location we get a maximum amplitude. So this is the anti-nodal point. Okay, this is the anti-nodal point. This is anti-nodal point. This is anti-nodal point, and we know where we get anti-nodal points, where when x is equal to lambda by 4, and next antinode is 3 lambda by 4. Okay, x equal to lambda by 4, x equal to 3 lambda by 4. So these are the our wave representation. So nodal point is like this. Then just to check what is the difference between adjacent nodal point. This is x equal to 0, x equal to lambda by 2. That means lambda by 2. Same like that, just to check what is the distance between adjacent antinodal point. One is x equal to lambda by 4, x equal to 3 lambda by 4. So 3 lambda by 4 minus lambda by 4 is what? That also lambda by 2. Then what is this is actually our node, and this is antinode. This is node, this is antinode, this is node, like that. So what is this difference? What is the distance between adjacent node and antinode? That is 0. This is lambda by 4. That means lambda by 4. Okay, like that. So this is happening in our amplitude. This is happening our amplitude. So this point we should remember what is that. So every particle. So what is happening in standing wave? Every particle. We should remember this one. Every point except few. Who is that? Except few. Except few means the nodal points. Okay, except few perform simple harmonic motion. Simple harmonic motion with a different amplitude. With a different amplitude. With a different amplitude. Okay, with a different amplitude. And this amplitude and this amplitude and this amplitude varies. This amplitude vary from students, vary from that a is equal to 0. This a 0 to a is equal to 2a. So this also very important. Every point except few perform SHM with a different amplitude, and this amplitude vary from amplitude 0 to 2a. Okay, so like that. The next we can discuss very interesting thing. That means we can try to visualize this standing wave. Okay, so for this, so what is this one? That is y versus x graph with respect to time. What is y? Y is a displacement of particle with respect to x. X is what? Position of particle from the beginning. So for this I need a graph. Okay, I need a table. Okay, first we can draw the table. This is omega t. Okay, omega t. The next one is, so first we can write our displacement equation. What is that? The y is equal to 2a cos omega t sin kx. This is our, I think this is our graph. Okay, sure. Students, sure? This is our displacement equation. Y is equal to 2a cos omega t, cos y equal to cos omega t sin kx. Okay, then so I'm going to draw the one table, that means omega t. Then I need this one. The next one is this one, 2a cos omega t. Then what is next one? Next is this whole y, this whole y value. Okay, this whole y value. Okay, like this. Then we can fill up the terms. When omega t, when time is equal to 0, when time is equal to 0, what is our 2a cos omega t? What is our 2a cos omega t? Cos omega t, cos 0 is 1, then 2a. So this expression is 2a. That means this term becomes what? 2a. So what is our y value? Y value is 2a sin kx. 2a sin kx. Then omega t, next omega t is the angle, next angle is 30 degree. 30 degree means pi by 6. So that means what is this one? 2a cos pi by 6 is what is that? Cos pi by 6 is root 3 by 2 into 2a, we get root 3a. So at the time what is our y expression? That means root 3a sin kx. The next thing is what? Next thing is our 45 degree pi by 4. Cos pi by 4 is 1 by root 2 into 2a is what? Root 2a. Root 2a. Then our expression become, our displacement expression become root 2a sin kx. Sin kx. Okay. The next one is, next angle is our 60 degree. What is 60 degree? What is 60 degree? Pi by 3. So 2a cos 60 is actually what? A. Then our displacement equation become a into sin kx. The next angle is our pi by 2. 9 cos 90 0. So this is 0. Okay. The next one is 120 degree. 120 degree means 2 into pi by 3. So just to put here 2a cos 2 pi by 3, what we get? We get minus a. Then our expression become minus a sin kx. Okay. The next one. The next one is 135. 135 is actually 3 into pi by 4. Okay. 3 into pi by 4. 3 into pi, just to put here, we get what? Minus root 2a. Minus root 2a, that is minus root 2a sin kx. Okay, students. The next one is, next one 150. 150 is actually 5 into pi by 6. Okay, 5 into pi by 6. Then just to put this value, you will get minus root 3a. Okay, so our displacement equation becomes root 3a sin kx. Root 3a sin kx. The next one is our 180 degree. 180 degree. 180 degree means our pi. If it is 180, what is our expression? This become minus 2a. Then our displacement equation becomes minus 2a sin kx. Then I am going to draw the diagram. The diagram is very, just to try to visualize. Okay. So look here, this is a sin kx graph. So when we get a nodal point, when sin become 0, when sin kx become 0, when we get sin kx become, we already found. So at these locations and at these locations and at this location. Okay, at this location. That means when x is equal to 0, when x is equal to 0, at these locations, when x is equal to 0, or x is equal to lambda by 2, or x is equal to 2 lambda by 2, that is lambda. In these values, we get a 0 displacement. That means particles are at rest. Then at a time is equal to 0, what happens? Our displacement equation is 2a sine kx. How we can draw the sine graph? 2a sine kx, how we can draw? Students, how we can draw? Like that. Just draw this one also. Then just draw sine 2a sine kx like that. Like that. That means this is when time is equal to 0. Then this is our sine graph. What is amplitude? Amplitude is 2a. This amplitude is 2a. This amplitude is 2a. Okay? This amplitude is 2a. This amplitude is 2a. The next one, when omega t becomes pi by 6, when omega t becomes pi by 6, what is the value expression? Root 3a sine kx. Root 3a sine kx. How to draw? Like that. Root 3a is the amplitude. Like that. When omega t becomes pi by 6. Pi by 6. So what is the amplitude? Amplitude is root 3a. Amplitude is root 3a. Okay. The next one, when omega t is equal to pi by 4, what is expression? Root 2a sine kx. Root 2a sine kx. How to draw? Like that. Amplitude is root 2a, like that. So omega t is equal to pi by 4. Omega t is equal to pi by 4. The next one. So this just to mark this amplitude, this is root 2a. Okay, root 2a. Then next one, pi by 3. At pi by 3, what is the amplitude? What is the sine function? A sine kx. Okay, a sine kx. That means like that. Like that. This is when omega t is equal to pi by 3. Omega t is equal to pi by 3, and this amplitude is, we can write a. Okay, like that. Okay, yeah, like that. Like that. Okay. The next thing, when omega t becomes 0, what is the displacement? Displacement like this. Like this. So that means this is our omega t is equal to pi by 2. So what is happening? What is happening? Initially, all are at the extreme position. All are at the extreme position initially. Initially, all are extreme position tends to move towards like that. That means we already discussed one point. What is that? Everyone has a different amplitude, but initially everyone at the extreme position with a different amplitude. Amplitude is different, but everyone at the extreme position. Okay, here also extreme position. So just okay. So what we can say that? So from this, what we can say? That means just look this loop. In a single loop, everyone at one extreme position, same extreme position. So then what is the phase difference? Phase difference of particle in the same loop? 0. Then this one, this is also at extreme position. This is adjacent loop. This is the adjacent loop, but this is at the other extreme position. So what is the phase difference between particles in adjacent loops? That is pi. One is one extreme and another one is other extreme. Okay, so like that. Then like that it happens. Like look here. Like that it happens. Like that it happens. Okay. So initially like this, then it go like reach at here. Then we can check at 2 pi by 3 what is happening. At 2 pi by 3 what is happening? Like that. At 2 pi by 3 what is that? Minus a sine kx. So our graph is like that. That means when omega t is equal to 2 pi by 3. The next one, at 3 pi by 4, what is the expression? Minus root 2a sine kx. That means how we can draw? Like that. Omega t is equal to 3 pi by 4. Okay, the next one. When at 5 pi by 6, what is the value? Minus root 3a minus root 3a sine kx. So we can draw like that. So try to visualize, students. Try to visualize. So this is omega t is equal to 5 pi by 6. 5 pi by 6. Then next one. At pi, what is the expression? Like that. So what is happening? What is happening? So it is oscillating with a different amplitude. This is oscillating with a different amplitude, and this try to visualize like initially like that, then like that. It is okay. So only there is no motion towards forward. Okay, energy is only reside in this or energy confined in this region, but there is what is happening? What is happening? But particles are oscillating about their own position with a different amplitude, and this is at maximum amplitude. So this point is known as nodal point. This is the minimum amplitude. There is no, that means 0. This is at always at rest. Just to check, always at every time this is at nodal point is at rest. Nodal point is at rest. So that is a y-x graph with respect to time. Very interesting like that. Like that it happens. Like that it happens. Okay, always confined in this region. Energy is always confined in this region. There is no energy is moving forward like a traveling wave. That's why this is a stationary wave. Okay, students, hope it is clear. Okay, so I'm going to check. So only one wave is possible? No, we can check. Okay, so I have introduced one wave, then I am going to check another possibilities. Okay, so second possibility, that means other possibility of other possible standing wave. Okay, so first one, like that. It's a string, and this is string is fixed at a rigid end. Okay, string is fixed at a rigid end like that. String is fixed at a rigid end. String is fixed at a rigid end, and one ray is developed here, and this is what y1. Okay, so if this is incident at a rigid end, what happens? It face advantages by pi, we already discussed, and this is our y2. This is our y2. So just to try to do then just try to do our superpositions. What is y1 value? That is equal to a sine kx minus omega t. Then what is y2? That means this is the reflected wave at a fixed end. So minus a sine, direction is opposite, kx plus omega t. Just to try to add. Okay, so you will get y is what? You will get this expression y is equal to 2a. Okay, 2a cos kx. Okay, cos kx. Just apply our trigonometric operation. Finally, you will get 2a cos kx into sine omega t. So do you remember our previous expression? So it is just there is some difference. So a small difference is there. Okay, between them. So this is the another possible expression. Another possible expression. So I am going to draw this one. So in here, so sine kx. Okay, 2a sine kx. What is that? What is that? This is actually amplitude. This is the amplitude. Sine 2a sine kx. This is the amplitude of this wave and sine omega t. So at x equal to 0, what become? Cos kx is 1. So what is amplitude? 2a. So at x equal to 0, if cos kx is present, then x equal to 0. That means at the beginning point, what we get? We get 2a. That means what is 2a? That's an anti-nodal point. Very, very important. Anti-nodal point. So I am going to draw this graph. That means if this is the, I am going to draw that. Okay, we know this is a anti-nodal point, and this, so this is the nodal point. Okay, this is actually x equal to 0. Then this is x is equal to lambda by 4. This is a nodal point. How to check? just apply. When we get a cos kx is 0, just that's only the thing. You get x equal to lambda by 4. Next till this one is 3 lambda by 4. 3 lambda by 4 like that. Okay, that means this is our nodal point. Our graph will be like that, like that. Okay, this is the nodal point. This is the antinodal point. This also antinodal point. Okay, maximum. So in next time you get like this, the standing wave like this. Okay, so this is another antinodal point. Okay, this is another antinodal point. But these two are nodal points. Okay, because amplitude is 0, like that. Then next one. So what we can say, when x is equal to 0, what we get? We get amplitude is, the amplitude of the resultant wave is 2a. That means at x equal to 0, what we can say? We can say this is the antinodal point. Okay, this is the antinodal point. Okay, antinodal point. That means when kx term is come, at the time this become x equal to 0 term become antinodal point. Okay, the next one, when time is equal to 0, when time, just to here, just to draw the here, when x is equal to 0, we get what? Antinodal point. Antinodal point. The next one, when time is equal to 0, when time is equal to 0, that means at the initial time, when sin 0, what happens? This sin 0 is 0, so whole term becomes 0. That means all at the mean position. Time equal to 0 means all particle initially at the mean position. So particle start from, all particle start from mean position, start from mean position. Okay, so how we can draw the graph? Initially all are at the mean position. All are at the mean position. Then after that, what happens? This is a 2a cos kx sin omega t. We get like that. Then this is at t equal to 0. All at rest. Then after that, after some time, we get like that. Graph is like that. That means when t is equal to t. That means initially all are at mean position. Then this is moving, start to moving upward. This is start to moving downward. This start move upward. That means we can say like that. Initially like that. Okay, like that. And time goes on, it reaches at its maximum point. Okay, and time goes on, it reaches at its maximum point, like that. Like that. Okay, that means it's going like that, it's going like that, it's going like that. What is that time? Time is equal to t by 4. From mean position to extreme position, what is the time? 1 by 4 of the time period of the wave. Okay, like that. So this is the second possibility. I am going to discuss the third possibility. Just imagine this is a wave. Okay, this connected at free end, okay, or loose end, connected at loose end. This string is connected at loose end. And if a ray, that means a wave is generated like this, similar to a cos graph. Okay, then it is a loose end. So this also like there is no phase difference. So if this is y1 and this is y2, it's y1 and y2, similar to a cos graph, not a sine graph. So how we can draw our y1? Y1 is equal to a cos kx minus omega t. Then how we can draw our y2? Y2 reflected wave. This is at a reflected at free end. So a cos k x plus omega t. So just add these two. Just add these two. Finally, you remember this one. We get like this: 2a cos kx into cos omega t. Cos kx into cos omega t. So finally, we get like that. So this is the the third possibility. This is the third possibility. And what is this one? 2a cos kx. That is the amplitude of this wave. This is what? This is the amplitude of this wave. This is the amplitude of this wave. This is the resultant amplitude. Resultant amplitude. Okay, resultant amplitude. So when x equal to 0, what? Cos kx is 1. So resultant amplitude is 2a. That means when x is equal to 0, result amplitude is 2a means that is a antinodal point. So when kx is came, at the time what we can say, that is a antinodal point. Okay, antinodal point. Antinodal point. Then when time is equal to 0, what happens? So cos omega t is 1. So our expression is 2a cos kx. That means what? That means what? When time is equal to 0, everyone at the extreme position. That's similar to a cos graph. So everyone at the extreme position. That means all particles start from extreme position. So I'm trying to draw. So let's draw the graph. Like that. This is our reference line. Okay, reference line. This is x equal to 0 is a nodal point, antinodal point. So this is our x equal to 0. Okay, x equal to 0, and this is our x equal to lambda by 4, antinodal point. So next antinodal point is lambda by 4 plus lambda by 2. Okay, adjacent distance between nodes, that is 3 lambda by 4. Then initially all particles start from extreme position, or at a time that means time is equal to 0. What is the graph? This is 2a cos kx. How to draw 2a cos? Like that. This is when time is equal to 0. This is a graph, starting time. So every particle has a tendency to move like that. And this one, we can draw this one also. Like that. Okay, like that. So at a time, so other time what happens? After some time what happens? It like that. When t is equal to t, that means it go like this. Like that. Okay, like that. Is it clear? Like that. Okay, this is the third possibility. Then I am going to check our fourth possible case. That means this is a string. String is connected at a fixed end. Okay, string is connected at a fixed end. Okay, then if a wave generator like that, okay, it's a cos graph. Okay, similar to cos graph. Go like this. It's a y1, and this is a fixed end. Okay, it's a fixed end. So what happens? It will be reversed, or there is a pi phase angle difference between them. So this is our y2. Okay, then so what is y1, students? What is y1? It's a cos graph. y1 is a cos omega t minus kx. Then what is reflected wave? We know minus a. There is a phase advantage by pi. Cos k omega t plus kx. Just add these two. what we get? We get like this resultant wave like this. Okay, that means 2a sine kx into sine omega t. This is the resultant standing wave. This is the fourth possibility. This is the fourth possibility. In here, what is the amplitude? What is the amplitude? 2a sine kx is the amplitude. 2a sine kx is the amplitude. This is the amplitude. This is the amplitude. Okay, this is the amplitude. Amplitude is equal to 2a sine kx. Then just to check at x equal to 0. Just to check at x equal to 0. At x equal to 0, what happens? At x equal to 0, sine kx is equal to 0. That means at x equal to 0, that is a nodal point. That is a nodal point. Okay, we got that point. X equal to 0 is a nodal point. When sine kx is come, then x equal to 0 is a nodal point. When cos kx is come, when x equal to 0 is the anti-nodal point. Then when time is equal to 0, when time is equal to 0, when time is equal to 0, what happens? Our sine omega t becomes 0. So all, what is the displacement equation at time equal to 0? 0. That means every particle at mean position. So every particle, all particles start from mean position. From mean position. Okay, every particle start from mean position. So how we can draw like that? This is our reference line. Okay, nodal, what is a nodal point? Just to mark the nodal points. X equal to 0 is the one nodal point, x equal to 0. Then x equal to, next one is x equal to lambda by 2. The next one is x equal to 2 lambda by 2, that is lambda. These are the nodal points. Okay, these are the nodal points. Then at all particles start from mean position at time equal to 0. So we can say at t equal to 0, every particle is at here. Then after some time, what happens? After some time, what happens? It go like this. When t equal to t, that means what time? When t equal to t. Okay, that means initially every particle try to move like that. Okay, and at a t by 4, it reaches at a maximum amplitude. Every particle reaches at its extreme position when t is equal to t by 4. Okay, that means time taken to reach extreme position from mean position is actually half 1 by 4 of the quarter of the time period. That's we know. So this is happening. These are the 4 cases. So not then. So in general we can say, so in general so we can check whole scenario. Okay, in general we can say like that: the y is equal to 2a sine kx into cos omega t, or the next possibility is actually what? That means 2a sine kx into cos kx sine omega t. Okay, the next, what is the next possibility? 2a cos kx into sine omega t. The next one is what? 2a cos kx cos omega t. These are the four possible standing wave. Then this, and the in this thing you should remember, this one is our amplitude. This one is our amplitude. That means this is the amplitude. This is the amplitude. Okay, in here this is the amplitude. In here this is the amplitude. In here, this is the amplitude. So in general, okay, student, this is important. So in general, we can like that. So if y is equal to 2a into cos kx or sin kx, okay, just to check these expressions, sin kx, okay, sin kx into cos omega t or sin omega t. These are the possibilities. These are the possibilities. Okay, these are the possibilities. In here, if sin kx is come, then what we can say, x is equal to 0 is actually, x equal to 0 is actually what? X equal to 0. X equal to 0 is the, x equal to 0 is the nodal point. Okay, x equal to 0 is the nodal point. And in here, if cos kx is come, at the time we can say what is x? X equal to 0 is anti-nodal point. Okay, anti-nodal point. Anti-nodal point. Okay, the next one, in the case of this one, in this expression, when sin omega t is come, then t equal to 0. That means at t equal to 0, sin omega t 0. That means all particles starts from mean position. If cos omega t is come at the time when time is equal to 0, what we can say? We can say that all particles start from extreme positions. All particles start from extreme position. So in general, we can write like that. Y is equal to 2a into cos kx or sin kx into cos omega t or sin omega t, like that. Okay, very important. Then we can discuss our application. Okay, we can discuss application. Okay, problem. Wait. No. So we can discuss application. Okay, application of this one. How to, when we need this one. Okay, so in general, look here. In the case of guitar, just draw a guitar. In the case of guitar, okay, a guitar. Okay, this is a string. So this is a guitar. So just to check what is happening in here, this end is fixed and this end is fixed. So when we touch this string, what happens? We can hear a noise. How? Actually, look here. So this is a fixed at both ends. So in a guitar, so in here, standing wave will be produced. By this standing wave, we get the tuning, we get the sound, sound. Okay, so this is a guitar. In the case of guitar, just to consider in the case of flute. Just to consider a flute. Okay, so these are the holes. So in here, what this is open end, this is also open end. So in here, both the ends are open, or both the ends are anti-nodal point. In here, both the ends are fixed and both the ends are nodal point. So in the another case, the clarinet, in the another instrument, just imagine another instrument like that. So another musical instrument, okay, is another musical instrument. In this case, this one is closed end. Okay, this one is closed. and this one is open. So in this musical instrument, okay, so we get a different sound by using this standing wave. So in here both ends are closed. Both ends are closed. Okay, both ends are closed, and in here both ends are open. Both ends are open. In here this end is closed and this end is open. Okay, that means A end is open and other end is closed. So in this whole situation, other end is closed. That means in these three situations we get a different type of standing wave. Okay, different type of standing wave. So before going to that section, okay, you just remember this one. Okay, you just remember three terms. Okay, that means you just remember, just note that points. That means these 3 points. That means the minimum frequency. The minimum frequency is generated. Minimum frequency is generated in an instrument. Is known as what? Fundamental frequency of that instrument. Okay, that is actually fundamental frequency of that instrument. Okay, that's thing you should note. The next point, the minimum frequency is generated in an instrument is known as fundamental frequency. The next point is what? The frequency higher than this fundamental, higher than fundamental frequency is known as what? Frequency is known as what? That is a overtone. Okay, that is overtone. The third term is the frequency which are integral number of fundamental frequency. Integral number of fundamental frequency. Okay, integral number of fundamental frequency. Frequency is known as what? That is known as harmonics. These three things also you should remember. Then I am going to consider the situations. Okay, so if minimum frequency is generated in an instrument is known as fundamental frequency, the frequency which is greater than fundamental frequency is known as overtone, and if this greater frequency is the integral number of fundamental frequency, then that is known as harmonics. Okay, so we can discuss the situation. If both waves are closed, not waves, sorry, this is both ends are closed means in the case of guitar and sitar. In the case of sitar and guitar, if the both ends are closed, at the time what happens? Okay, we can check. So first let me draw a diagram. Wait. If both the ends are closed, okay, both the ends are closed. So what will be the minimum frequency? Sorry, what will be the minimum frequency? How to draw like that? This is the maximum wavelength. Okay, in here. So next time we get like that. And and this is the what length. This is the length of that instrument, guitar or sitar. So length. So this length is equal to, this is a half of the wavelength. What is that? Half of the wavelength, lambda by 2. Okay, half of the wavelength, lambda by 2. So so what is lambda here? So lambda here, lambda is equal to 2L. So what is the frequency? So this is this way. What is the frequency? This frequency is the minimum frequency. That means when you touch the string, so if the touch with a little force, at the time it will be generated. So this is a minimum frequency. At the time you hear some sound. So that F1 is actually what? That is the velocity of the string divided by lambda. What is the velocity of string? That is 10 root of tension into mu. What is mu? Linear mass density into 1 by lambda. What is 1 by lambda? 2L. So this is actually what F1 is known as. What is the minimum frequency? What is the name? That's a fundamental frequency. What is that? This is known as fundamental frequency. Or other thing, this is also integral number of fundamental frequency, means this is the first harmonic. Okay, first harmonic. I am going to consider another case. That means due to our disturbance, if the wave is formed like that, just to check, just imagine, due to our disturbance, I am disturbing the wave string. If it is formed like that, wait. If it is like that, so what is the length? This length of this instrument is equal to what? This is the lambda by 2. So this length is equal to what we can say? Wait. This length is equal to 3 lambda by 2. So from this what we can say? So what is lambda? Lambda is equal to 2L by 3. Okay. This is lambda by 2. This is lambda by 2. This is lambda by 2. So 3 lambda by 2. Okay, if both ends are closed. So what is our fundamental what is the next frequency? F1. What is F2? Lambda by 2, 3 lambda by 2. So lambda is equal to 2L by 3. So our fundamental, this frequency is equal to 3 divided by oh wait, I made one mistake. Sorry. So in here, look here, like this. What is the next possibility of wave formation? Like that. Okay, like that only. Okay, so I have drawn the third case actually. Okay, then next one. So what is the length of this instrument? This length is equal to lambda by 2. That means 2 lambda by 2. So what is lambda here? From here, in here, what is the new lambda formed? New lambda is equal to 2L by 2. Okay, then what is the new frequency? What is the F2? Our second possible frequency, that is equal to velocity, that is T by mu, tension is T by mu, then divided by lambda. Lambda is equal to 2L by 2. So F1 is 1 by 2L into T by mu, and F2 is 2 by 2L into T by mu. And so this is known as our second harmonic, because this is a second integral multiple of fundamental frequency, second harmonic. Okay, or second harmonic, or this is our second harmonic, or we can say this is the first overtone. First overtone. Okay, like that. Like that, this is the one situation. If both ends are open in the open organ pipe, if the both ends are open, this is another case. Then the third case is if A end is open and other end is closed. This is the another third case. Then we can go to the problem section. So this is a single question, but I have considered the whole situation. So just to read the question. The vibration of a string of a length is 6 centimeter. That means string of length is 6 centimeter fixed at both ends are represented by the equation of y is equal to sine pi x by 15 into cos 96 pi t, and where x and y are in centimeter and t in second. Okay, then we have to find what is the number of loops formed in vibrating string will be. We have to find how many loops are formed here. Then second thing, where are the nodes located along the string? We have to find the nodal points. Then third one, find the phase difference between x equal to 10 centimeter and x equal to 20 centimeter. That means at the position 10 centimeter and 20 centimeter, we have to find what is the phase difference between them. Okay, then the fourth one is what is the maximum displacement of point at x equal to 5 centimeter. That means we have to find maximum displacement, mean we have to find amplitude of the particle at x equal to 5 centimeter. Then the fifth one is what is the velocity of the particle at x equal to 7.5 and at t equal to 1 by 4. T equal to 1 by 4. Then write down the equation of component waves whose superposition gives the above wave. We know standing wave is formed by the superposition of two traveling wave. We have to find that two waves by just looking this one. So this is our wave. Wave is y equal to 4 sine pi x by 15 into cos 96 pi t. Okay, then so we can start the problem. What is our wave expression? So y is equal to, what is our wave expression? Y is equal to 4 sine pi x, 4 sine pi x by 15, then cos 96 pi t. This is our standing wave equation. So what we have to find? The number of loops formed in the vibrating string will be, and we know length is given, length is 6 centimeter. Okay, so if both ends are closed means this will be like that. Just imagine if there is a n loops. Okay, n loops, and this length is given. What is this length? Length is L. If there is a n loops like that, then L is equal to n lambda by 2. So n is what? N is the number of loops. So if you can find lambda value, because L is known to us, lambda we can find from this expression, then we can easily find n value. Just to try that. So this is actually what? Pi by 15x means that is a kx. Okay, so what is k? We know k is actually 2 pi by lambda. Okay, that is equal to pi by 15. So pi will be cancelled. What is lambda? lambda is equal to 15 into 2, that is 30 centimeter. So this is the lambda of this wave. Okay, this is the lambda of this wave. This is the lambda of this wave. Okay, that means wavelength of this wave. Then, so just to put this one, L is what? 60 centimeter. That is equal to n into what is lambda? 30 divided by 2. So this 2. So what is n? N is equal to 4. That means 4 numbers are there. 4 loops are formed. 4 loops are formed. Okay, students, 4 loops are formed like that. Like that. How many loops? N is equal to 4. N is equal to 4. This is our first question. What is this is the first question. What is the next question? Where are the nodes located along the string? Where are the nodes located along the string? So in here sin kx is come. So when sin kx is come, where are the nodal points? We know x is equal to n lambda by 2. That means when n is equal to 1, 0, then this is 0. And next possibility is lambda by 2. Next possibility is lambda, 2 lambda by 2, and so on. Okay. So lambda value we know. What is lambda? What is the lambda? Lambda is 30. So that x values are 0. Lambda by 2 is actually what? Lambda is 30, 15. The next one is next double, this double 30. The next one 3 lambda by 2. What is that? 45. Then 60. Then only length is up to it has only 60 centimeter. So these are the nodal points at these locations. Okay, these are 0 centimeter, 15 centimeter, 13 centimeter, 45 centimeter, and 16 centimeter. At these locations, nodal points are formed. Okay, this is our second point. Then third point, find the phase difference between x equal to 10 centimeter and x equal to 20 centimeter. Very, very nice problem. Okay, that means this is our frame. Wait. This is a one nodal point. This is the another nodal point. This is the another nodal point. When x equal to 0, when x equal to 15, when x equal to 30, when x equal to 45, when x equal to 16. In these positions, nodal points are formed. When the phase difference between x equal to 10 and x equal to 20. X equal to 10 means at this at here. Okay, at here. Then x equal to 20 means in between 50 and 30 at here. So we know one thing. What is a phase difference between the particles in the same loop? 0. What is the phase difference between the particles of adjacent loops? Pi by 2. So this x equal to 10 is at one loop and x equal to 20 is the adjacent loop. So what is the phase difference between them? Phase difference between them, that del phi is actually pi. Don't do this expression. That means our del phi is equal to 2 pi by lambda into delta x. Don't do this one. Okay, don't do this one. This one is for traveling wave. This one is for traveling wave. Okay, this one is for traveling wave. Then What is the maximum displacement of a point at x equal to 5 centimeters? So at x equal to 5 centimeters, what is the maximum displacement? They are asking what is amplitude. Okay. So so what is amplitude here? 4 into what is amplitude? 4 into sine pi x by 15 is the amplitude. Okay. 4 sine pi x by 15. This is the amplitude. It varies with the x value. So at x equal to 5, just to put x equal to 5, 4 into sine pi into 5 by 15, that's pi by 3. Pi by 3. Pi by 3, sine pi by 3. Root 3 by 2 into 4. That means 2 root 3. 2 root 3 centimeter. This is the amplitude. This is the amplitude at x equal to 15 or maximum displacement. Okay. The next question. What is the velocity of particle at x equal to 7.5 centimeter and t equal to 0.25 second? That means at 1 by 4 second. So what is our expression? Our expression y is equal to 4 into sine pi x by 15 into cos 96 pi t. This is our expression. So at x equal to 7.5. So x is equal to 7.5. What is our expression? This becomes 4 into sine pi into this 7.5 by 15. What is that? Pi by 2 into cos 96 pi t. That means this y is equal to 4, sine pi by 2 is 1, so cos 96 pi t. So at x equal to 7.5, what is the y value? What is the displacement of the particle? That equal to 4 into cos 96 pi t. That means with respect to time, that position will varies. So what we have to find? We have to find velocity at time. Okay? Just to differentiate this one. So we get velocity of particle. What is that? 4 into 96 pi t negative, so cos, okay, sine 96 pi into t. Okay, this is the general expression for velocity. Okay, this is the general expression for velocity. So when time is equal to 0.25, at the time what is the velocity? So velocity when time is equal to 0.5 or 1 by 4 second, 1 by 4 second, what we get? We get 4 into 96 pi sine 96 pi into 1 by 4. 1 by 4. Okay, 1 by 4. So what we get? We get 4 into 96 pi sine 96 by 4, 24 pi. So what is the sine of n pi? Sine of n pi, that is 0. Sine of n pi is 0. So this term is 0. So from this what we can say? We can say, so velocity of particle at x equal to 7.5 and at the time is equal to 1 by 4, that is 0. Velocity of particle is 0 means it's a SHM. So where does we get 0 velocity? At the extreme position. Where does it get? This is at the extreme position. That means particle is at the extreme position. Okay, particle is at the extreme position. That's why velocity is 0. Okay. The next one. The sixth question, last question. Write down the equation of the component waves. Write down the equation of component waves whose superposition gives the above wave. So we know how to develop standing wave from two component wave. So in here we know sin kx and cos omega t is present. At the time what is the value we know. Okay, So what is y1, or what is a y displacement equation of standing wave? That is given 4 into sine of pi x by 15 into cos 96 pi t. This is the displacement equation of standing wave. Just remember, this is our first case actually. Okay, this is our first case. So if it is 2a, so what is a? This is 2. So first equation y1 is equal to 2 into sine, okay, sine kx, that means pi by 15x minus omega t 96 pi t. Okay, this is a y1. Okay, then or we can convert into general form, that means like that, 2 into minus 2 into sine 96 pi t minus, just turn this one, pi x by 15. Then what is y2? What is y2? So in second case, yes, this is our first case. What is y2? 2 into sine, both are moving in same direction, pi x, or opposite direction, hit at free end 96 pi t plus pi x by 15. Okay, so this is the one y1, this is another component. By the superposition of these two waves, we get what? By the superposition of these two component waves, we get this standing wave. Okay. So we have discussed a standing wave, some situations, and we have done one problem. From this I try to add all the points. Okay, all the points, how to find the number of loops and where are the nodes located along, that means we have how to find the nodal points, then find the phase difference between them. Why, nice question. What is the maximum displacement? That means at a particular location they will ask what is the maximum displacement. Maximum displacement is what? Amplitude. Then what is the velocity of the particle at x equal to 7.5? We get easily at x equal to 7.5 we get the y value, that means displacement equation. Just to differentiate, at the time you will get velocity of particle. The next one, write down the equation of the component waves whose superposition gives. Maybe you may get some difficulty in this, the last question, but you just try to familiarize. Okay, I have introduced 4 cases, and okay, then try to familiarize that thing, then you can easily write these 2 component waves also. Okay, so students, hope you are fine, hope you get all these thing. Okay, so I'm winding up today's session. Okay, wait. Okay, so thank you.